to post it up on YouTube after, if you want to share it with other people. I know that we just started winter break here in Hawaii, so a lot of schools and teachers are probably on winter break mode, but thank you again for everyone that's joining here today. This is our agenda for today. So my name is Adria. I work at the Hawaii Space Grant Consortium. I'm going to be going over session 1 of today's webinar. Session 1 will take approximately 50 minutes. And then we're going to take a 5-minute break or so and then return back for Kelsey's portion for programming and also intro to sensors using VEXcode IQ. All right, so let's get started here. So again, my name is Adria Fung. I'm the robotics education specialist here at the Hawaii Space Grant Consortium. Pretty much my whole background has been in robotics. I was a student on a first robotics competition team, competed throughout my 4 years of high school, eventually went on to get my robotics engineering degree at NASA Ames Research Center. And then I eventually got my master's in curriculum studies at the University of Hawaii at Manoa. And then pretty much I was a volunteer judge at various robotics tournaments here in Hawaii and also on the United States mainland. And then most recently, I was a middle school robotics teacher and also robotics coach at St. Louis School, where we traveled to various US Open, World Championships, and also international competitions. So pretty much live, breathe, went through robotics. And that's kind of like my entire life. Really, really fun experience. So, all right, so kind of let's get into the notebook. So this whole webinar of what I'll be presenting to you folks today can be used in both the classroom as well as in the competition aspects. And so in the engineering notebook is the great way of getting students started in kind of documenting their robot process as well as their build and programming. So I like to look at it as a how-to guide or manual for students. And it's a resource that the students and also future students can always refer back to. You can kind of almost look at it as like a yearbook in the very end, or it's like a progression of the robot's build and also programming as well. And so I'm going to be going over kind of a really quick sample of what an engineering notebook looks like. It's a very, very brief, but it's more so to give you guys the sense of how to organize an engineering notebook. And so this is a digital format of the notebook, but of course you can use a very similar organization for a physical notebook as well. So this is our title page for it. The first section of the engineering notebook is of course our table of contents. So you always want to start with a table of contents. If you're using a physical book, I like to leave about 2 pages back and front, which equates to about 4 pages of writing space. So I'm not going to go into the details, of course, of the table of contents. I'm sure all of us know what a table of contents looks like. But going through table of contents, after that, I like to ask the kids to give themselves an introduction, a team member introduction. Who are the team members on the team? And what are each of their respective roles on the team? And then next, of course, is to talk about the game strategy. How is the game being played? How do you score points? Maybe even the diagram of the field, just to visualize for the students exactly what exactly is the objective of the game. All right, and so let's kind of get into sort of the meat of the engineering notebook. So I like to organize or have the students organize it by competitions. So looking at each iteration of the robot design for every single competition that they do. So for every single competition section, I would ask them to break down to the build and also the programming sections of the actual organization itself. So for example, this is competition 1. This is the build section of competition 1. So we go into, of course, the very first thing to ask the students to do is to look at initial game strategy. So exactly how do we want to play the game this year? Asking the students exactly what is your game strategy and breaking it down. Sometimes you might have some students who are very overambitious and they want to do it all, but especially for the younger and newer students, maybe just breaking down to see, just focusing on just doing one thing and doing it very, very well. So again, this is an example of a very basic notebook, and I'm not going to go into too much detail. I'm sure all of us know pretty much how VEXIQ pitching in is being played. But again, I wanted to give you a broad overview of how to organize it that will help and aid in the students' learning and design process. So we start off with a game strategy, then asking the students to start designing an initial robot design to play that specific game strategy. So breaking it down of drive base and all the mechanisms that the students will be designing. So mechanisms like an intake, a launcher, a hanging mechanism, things like that. All right, so once the students have that initial robot design, then I'll ask them to actually go in and prototype each mechanism. And so prototyping, of course, gives that student sort of the learning process, that design process going into it. Let's prototype each one and then test it out to see if it actually works or not. So I would ask them to do a prototype mechanism for the engineering notebook and have it labeled as every single mechanism in the notebook. So this would be the drive base prototype, the lift prototype, the hook prototype, intake prototype, and also the bucket prototype. So this is just, again, an example of what it kind of looks like. And so after, of course, going through all the prototyping, then that's when the students start to, in their actual build itself, figure out what exactly will our final robot actually look like. And so hopefully after all that prototyping of all the mechanisms, they'll actually get to design that final robot. So in the very kind of last section of the build section would be the final robot and final mechanism. So again, having the students take a picture of their final robot design for that competition. And then I would ask them to break down each mechanism on its own page with pictures of that final mechanism that they do. And that was pretty much it for the build section. And of course, you would have an accompanying programming section for that first competition. So it's kind of the same thing. For the programming section, I like to ask students to start off, of course, with the teleoperated or the driver control if they have it for their robots. Again, I'm not going to go into detail of the code or anything like that. This is just the overview of an engineering notebook. After the teleop, we kind of go into autonomous. So exactly how do they want to set up their autonomous? Previously, my students had used Robot C. So this is kind of the part where I asked them to set up all of their functions and all of their variables. And so, of course, taking screenshots of code is good and putting it into their notebook. And then still within that autonomous section of it is the actual field or game strategy. So as you can see, this is a very great way for the students to visualize exactly how they want their autonomous strategy to work. So they use really good tools in Google Slides. So circling the balls that they want to intake, then going to the area where they want to gather more balls, and then hopefully shooting it into the high goal, of course. So great way of visualizing it, and also gives a really great visualization for the judges as well, who will be reviewing the notebooks too. And of course, once we have that strategy, I would ask the students, of course, put in your final autonomous code. So, and also talk about how that autonomous plays that strategy. So after, putting in all that code in there, you might use several pages to have your screenshots of your code. I asked the students to pretty much start recording some scores from your test runs. How did it work? Have a table out for your driver skills runs and autonomous skills runs. And so, of course, this is pretty much for the robot skills challenge of the VEXIQ game. And then after that, at this point, our team would then go into the competition, we'd perform, do as best as we can, and then come back. And then after the competition, I asked the students to have a reflection and write it down of that competition. So how well did they do? What did they think they did well on? And of course, how to improve for the next one. So it gives the students that sort of culminating conclusion of that competition up until the reflection point. And then of course, after that, we're going to repeat the same thing for our next competition. So of course, we want to emphasize to the students that this is that iterative design and learning process that we want them to go through. And so the same thing, we'll go through the same exact thing for, say, our second competition that we're going into. So again, I'm not going to go into too much detail. This pretty much repeats the same thing. So build section, if there's any kind of game strategy that we want to try out differently, maybe taking out some strategy, maybe adding some more things in. And then of course, initial robot design of that game strategy. And then after that would just be our prototype. So prototyping drive base. If they want to keep the drive base, have that explanation of why they want to keep that same drive base. If they have any new kinds of mechanisms that they want to try out, of course, prototyping every single one and documenting it in their notebook. So these are all the prototypes of the mechanisms that they want to go through, some sketches, and of course, some pictures if they have that's applicable. So, and then we come into, of course, our final robot for that second competition. And so what did they do differently? And of course, I would ask them to list out the mechanisms on the different pages as well. And so that's pretty much the conclusion of the build section of the second competition. And of course, we go through the same thing for the programming section. So the same exact thing as what we just talked about would be the teleop period, teleoperated or driver control code. Then also talking about, of course, the autonomous, anything that's changed, another description about the autonomous, setting up the autonomous if you have any variables, any functions for the students to set up. And of course, again, game strategy, if there's anything different that they want to improve on their autonomous game strategy. Sometimes if we have multiple autonomous codes, I like to ask the students to have different strategies laid out. So there might be like 3 pictures of this field here that you see, but all of it with like different kinds of flow of where the robot is going to, depending on, the amount of points that the students want to score during the autonomous period. And then of course, having screenshots of the autonomous code in there. And then of course, our scores from our test runs again. And then again, at this point, we would be going into our second competition and then doing, really well and all of that. And then coming back, asking the students to reflect and review about that competition. So how well did they do? Anything that they want to improve on for the next one. So again, the cycle can repeat over and over again, depending on the number of competitions that the students go to. And sometimes I like to look at it as it's okay to be testing it on your own in the classroom and also reviewing it using a design matrix. But I think we all know that the best testing is really through the competition itself, is seeing how well our robot will perform in the constraints of the competition. That's honestly the best test for the students to go through. And so I'll give a quick overview as to what we kind of just talked about. So this is like the big picture overview of what we went through and the organization structure of kind of a nice iterative engineering notebook. So of course, we start off with the table of contents. The second section is the introduction of the team and also introduction of that year's game. And then all the other sections after that would just be that iterative design process. So competition 1, you would include the build section. And then under the build section would be game strategy, that initial robot design, some prototypes, and then of course, the final design of your robot going into that first competition. The second section would be, of course, the programming section. So looking at the driver control or teleop, and then going through autonomous, the strategy, and then as well as recording our test runs. And then the same thing, we just repeat the same thing all over again for competition 2. And of course, you can add more and more for every single competition or design iteration that the students go through. And so we see the cyclical process and we know it really well as the engineering design process. And so this is kind of what we want the students to be getting into, is going through this engineering design process, this cyclical design process, where they're going through all these designs and being able to reflect about it, figuring out what to improve on for every single competition, and going through that same thing all over again. And so if you go into the robot events or Robotics Education Competition Foundation, RECF's website, you're able to find a copy of the engineering notebook rubric. So this is pretty much out for everyone to go into and take a look at. This is actually used by the judges in reviewing notebooks at the events. And it's also a good rubric if you are a teacher scoring engineering notebooks for your classes, if you have the students do an engineering notebook for class. And so as you can see, I'm going to highlight it in yellow right here. this is the engineering design process. And so this is kind of like that really great cyclical process that the students can just go through. Of course, starting with identifying the game and robot design challenges and the goals. So that's like the strategy and all of that initial sort of brainstorming. And then we go through that actual brainstorming and prototyping solutions to it. Then selecting the best solution and plan, building and programming the solution, testing it out with the test results. And of course, repeating the same thing all over again for your next competition or your next robot design iteration. And so what we just went through was pretty much how do we structure that engineering design process into documentation in an engineering notebook for the students. All right, so that was pretty much it for the actual engineering notebook. So kind of let's dive into sort of the fun part of it, which is the build side of it. So we're going to start off with the most fundamental topic that I think is important for all students to learn about in VEXIQ, which is gear ratios. So this is a good way of learning the balance between speed and also torque. So torque is that rotational power. And so this is a great math application in robotics as well. And so for gear ratios, we know that you have a driver gear here, which is the one that's attached to the motor. So that is the input. Your output is your driven gear. And this is the one that's attached to either your wheel or your mechanism that you're running. And so the gear ratio is actually just that ratio or that fraction of output over input. And so with that ratio, if your gear ratio is less than 1, you would have more speed, but less torque or less power. If your gear ratio is greater than 1, you have less speed, but you have more torque or more power. And so, for example, for this one, this gear ratio is 60/36. So the numbers actually denote the number of teeth on the gears here. So you can actually see it on the actual VEXIQ gears. It'll label it as the number of teeth on those gears. So our driven gear is a 60-tooth gear, and then our driver gear is the 36-tooth gear. And so this ratio would then be 60/36. And then asking the kids to simplify it would be 5/3. And so therefore, you can then ask them, is 5/3 greater than or less than 1? So of course, it's greater than 1. So therefore, you would have less speed, but more torque. So if you need more torque or you need more speed, you would use compound gears. And so compound gears, you can stack them up level by level by level, and you would calculate each level's gear ratio first, and then you would multiply all the gear ratios together to get your final one. And so for example, let's take this one that this built one that we see here. So for the top level, we see that we have a 36-tooth gear to a 12-tooth gear. So our output is actually the 12-tooth one. So this is the one that we want that's attached to the mechanism or the wheel or the thing that you're wanting to output. The 36 one is our input. So for this top level, our gear ratio is 12/36 or 1/3. If we take a look at that bottom level, the bottom level that's right here. For the bottom level, if we break it down, it looks like this. So it's still a 12-tooth gear and a 36. So this 36 is the one that's attached directly to the motor, while the 12-tooth one is the one that's connected to this 36 one on the top level. And so therefore, for our bottom level, our output is actually our 12-tooth gear, and our driver is the 36-tooth. So therefore, our gear ratio would be 12/36, which equals to 1/3. So we have our top level and our bottom level. So then we go into it and we actually determine what is our resulting gear ratio. So our resulting one is the product of all the levels. So it'll be gear ratio 1 times gear ratio 2. So if we go back to it, our top level is 1/3. Second level is also 1/3. So 1/3 times 1/3 equals 1/9. And so 1/9, is it greater than or is it less than 1? So of course we know 1/9 is less than 1. Therefore we have more speed, but less torque. And so that's how you would calculate compound gear ratios. And so of course, gear ratios can still be used with sprockets as well. So if you look at the sprockets of from VEXiQ in your kits, you'll see the number of teeth on those sprockets, and you can then calculate the exact same thing. All right, so let's kind of go into that building fundamentals of it. So this is kind of what I like to start off the kids with. So looking at having a low center of gravity for your robots. So low center of gravity, meaning that your base should be wider and heavier at the lower part of your robots. And so how do we actually lower center of gravity? So you have to make your base wider and also heavier. So first off, how do we even make it wider? Which I would tell the students, you should probably make it almost the entire width of the size limit that you can go to. So that's how we would make it wider. And then how would you make it heavier? And of course, some students might say, oh, we'll just add counterweights, at the back or at the bottom and all, but no, maybe mounting something that's heavier and lower to the ground. So for example, things like your brain and your battery, and mounting it lower to the drive base. The second bullet is looking at the symmetry and using holes as a measurement for it. So of course, well, with VEXiQ robots, I asked the students to just kind of look at the symmetry of your robot and make sure it matches from left to right. And then of course, using holes as a measurement for it. So, how many holes do you want apart from the wheels? How many holes will it take in order to get to your next mechanism and things like that? Just making sure that it's the same from the left side of your robot and also the right side of your robot. And of course, using parts as with the appropriate function. So I like to go back to this beautiful poster that comes in all of the VEXiQ kits. Just making sure that we're using the parts with the appropriate function. So the beam should stay as structure parts, using gears appropriately, using standoffs appropriately, axles, and things like that. And then the three questions that I always ask my students as they're building is why, what, and where. So why are they building that specific thing? What are they going to use to build it? And where are they exactly putting it to, or where are they exactly mounting it? So these are kind of the three good reflection questions for the students to constantly be thinking while they're building their robots. All right, so let's go into drive bases. So drive bases are the base of the robot, and it's used to support all other structures that are on your drive base. So any kind of mechanisms that you have and things like that. So we can take a look. These are two configurations of wheel placements. And so think about it, like which one has a lower center of gravity? Would it be the one where the wheels are put on the center of the drive base where the holes are at? Or if it's at the top? So I think that's a good question for your students to figure out which one will give you a lower center of gravity. And so the four key criteria of a drive base that I like to introduce the students to is number one, the chassis shape. Whether you're using a rectangle or square chassis, U-shaped chassis or H-shape. These are the most basic chassis type of shapes that we see in VEXiQ. The second criteria is the number of motors, whether we want to use a 2-motor drive or a 4-motor drive. But we all know in the VEXiQ competition or VEXiQ challenge, we're very limited with the number of motors that we can use. So maybe, thinking about, maybe we'll just use a 2-motor drive and saving all of our other motors for all of our other mechanisms that they have to build. The third criteria is the types of wheels that the students will want to think about using. So maybe either Omni wheels or rubber tires, whichever one that you have, maybe even a combination of both. And then lastly, of course, is the power transmission, whether you want to use gears or sprocket and chain to power your wheels. And so let's talk a little bit more about the power transmission. So for the first one, gears on a drivetrain. So if students want to use gears on a drivetrain, kind of have to think about, all right, we need an odd number of gears, so the wheels will spin in the same direction, of course. Gears are definitely much more sturdier. You don't have to worry too much about the chain skipping. But it takes up a lot of holes on the beams that can be used for support structure. So if you take a look at this one, you can see that these gears pretty much run along the entire beam. And if you have axles running through it all, you might not have a whole lot of room to put your support structures above it, right? But gears are definitely a lot more sturdier. You don't have to worry too much about the chain skipping. And so take a look at this example that we see here. In this example, I have these the bigger wheels. These are not the standard 200 millimeter. These are the bigger ones. I had to use these big wheels because the Omni wheels and the regular size wheels are actually smaller than the diameter of the 60-tooth gear. So therefore, if you actually use the Omni wheels or you use the regular size wheels, these gears will actually be dragging on the ground. All right, so if students don't want to use gears and they want to use chain and sprocket, that's totally fine as well. Chain and sprocket on the drivetrain, some pros are that it's definitely easier to adjust if you want to adjust the distance between the two wheels. All you have to do is move the sprocket over or the sprocket over towards the end, and then just add a bit more chain to it. It frees up a lot of holes on the beam itself. So therefore you can add a bit more support structures and a bit more mechanisms on the chassis. The only con is that, of course, we know that chain might skip or even might break, especially you don't want that happening in the middle of your competition, which has happened in the past before with our teams. And so I've seen a lot of this in VEXiQ where teams are using 3 sprockets on their drivetrain. And so you have this big one here, and this is the one that's attached to the motor, and it's running across 2 smaller ones. Therefore, we know that this is going to create a faster speed on the wheels. So therefore, you would have a faster drivetrain, faster robots. But there has to be a balance between the amount of chain that's wrapped on the sprocket and also the chain tension as well. Otherwise, the chain could jump teeth, resulting in damage of the chain and or sprockets. And so kind of take a look. The yellow arrows that I have here are the actual chain wrap on the sprocket. So we're going to look at the different angles of each one. And so the smaller the wrap angle is around the sprockets, the more prone it is for the chain to jump teeth on the sprocket here. And so if we take a look at it, this bottom right one actually has the most wrap. So the most chain around that sprocket here. So as you can see, this angle is actually bigger than this angle that we have here on this bottom left side. So this bottom left actually has the least amount of wrap. So it has the least amount of chain wrapping across the sprocket. So therefore, it's going to be the one that's more prone to skipping or jumping. And so how do we actually combat this if students still want to use chains and sprockets, but they want a faster drive? So instead of using 3 sprockets, what I recommend to students is maybe using a combination of gears and also chain and sprockets. So the first step, of course, is to create a gearbox here. So we kind of just reviewed gear ratio. So creating a gearbox of the gear ratio or the speed of what the students want for their drive base. Then attaching the motor to the gearbox and then down to the sprockets, and then using 1-to-1 sprockets on the wheels. So the same sprockets on both wheels. So creating a 1-to-1 gear ratio across the chain, but then you have your gear ratio being created with the gearbox that we have here. As you can see, you can take a look. This chain wrap on the 2 sprockets, it wraps a lot more than the one that we saw previously in here. So therefore, if we have more chain wraps around the sprocket, it won't be prone to skipping or jumping teeth. And so I have a few more angles for you guys to take a look at. The top angle, as you can see, this is the gearbox that we have right here. And then the bottom gear, the output is the one that's attached to the sprocket and to the wheel. And so this is going to power, of course, with the chain and sprocket, powering the second wheel that we have in the front. This is a bit of a better angle that you can see. So this top one, the 60-tooth gear, is the one that's attached to the motor. The 36-tooth is the one that's our output, and with one single drive axle going across the sprocket and the Omni wheel. So that's kind of a good way for students to understand how do we use a combination of gears and also sprockets for a drivetrain. And the cool part is that they'll be able to see that this gearbox, you can actually customize it to whatever gears that you want to use for your gear ratio or your drivetrain. So they can always like, rip this out, put different kind of gears in, and then put this gearbox back along the same axle of the chain and sprocket. So kind of a cool way to customize to see what speed is better for the student's drive base. All right, so let's go into a little bit about mechanisms, aka subsystems that we have here. So mechanisms are everything else that is not the drive base, but it's used to play our game strategy and also scoring as well. So examples of mechanisms include our lift, claw, intake, launcher, and so much more. So let's take a look at this hero bot that VEXiQ introduced for this year's game. So if we count the number of mechanisms that they put on here, first one I see is this one right here, which is the intake to intake the balls. The second one is this launcher or this flinger that we have here. So in this robot, we actually have only 2 mechanisms on here. So as well as the drive base at the bottom. So some examples of a mechanism include a lift. So the 2 types of lifts that I like to introduce to beginning students are a 2-bar lift and also a 4-bar lift. So for the 2-bar lift on this left side, we see that whatever it's lifting up, whatever game object that this lift is lifting up is not parallel to the ground. It's simple to build because it's only using a single lever arm. So you would have the motor be on this rotating point, lifting up whatever it needs to lift up. But we know in a 2-bar lift that it's not going to be parallel to the ground. As opposed to this 4-bar lift, this 4-bar linkage will actually keep items parallel to the ground as the robot is lifting it up. The thing with a 4-bar linkage is that your height at this beginning part of it, so as we can see, we can even count 1, 2, 3, 4. So that's 4 holes, has to match what is at the very end here. So it'll be 1, 2, 3, 4. We skip this middle hole because it's like a off, 0.5 hole and all. And also the length needs to be the same too on all the bars. So you can have the students count the number of holes and match it to the bottom bar that we have here. So as long as this height matches the end height and the bottom bar is the same length as the top bar, you're creating this 4-bar linkage, which will keep your game objects and your items parallel to the ground. So this is kind of a cool way for students to figure out, all right, with a game strategy that I have, maybe in a previous VEXiQ game, do we want to keep game objects parallel to the ground, or do we want to keep it angled up as we're lifting it up? And so let's kind of go back to the building fundamentals of it. So we talked a little bit about lowering the center of gravity. We also talked about the symmetry and using holes as a measurement. So whatever you have on one side of your robot matches whatever you have on the other side of the robot. Sometimes I like to ask the students to think about your X, Y, and Z plane. So thinking about if it matches on your X plane, if it's flat, matching it, if it's on the flat side, Y would be your height and Z would be your depth. Using parts with the appropriate function, we want to make sure that the students are using wheels correctly. I've seen a lot of students use wheels as counterweights. I would say no to that. Try to design it so that you don't have to use counterweights. Using all the beams appropriately, using gears appropriately, sprockets, chains, motors, and standoffs, and much more in the VEXiQ kits. And then of course, the 3 questions to ask the students: why, what, and where. So why exactly are the students building that? What are they going to use to build it? So what parts are they going to use? And of course, where are they mounting it on the robot? Where is it going to go? And so let's take an example of this hero bot here. We're going to take a look at the symmetry of the robot. So what exactly are we talking about when we talk about symmetry? So looking at it where it's the same width across the length of the mechanism. So we're going to take this area that's just right here. And maybe some kids might be wondering, oh, why do we need collars over here? Why is there no collar over here? So if we zoom in and look at it a little bit more closely, we're going to start in the beginning right here. So this is where the motor is at. And so with the motor, we have a beam that's running across here to the intake. Then we have another beam that's here supporting that. We have the pulley, and then we have a beam that's at the end right here. So of course we know that this pulley is going to be powering this other pulley here, which is going to power this intake on. And so with that, these pulleys actually should be along the same width of this robot so that they're pretty much running straight. And so as you can see for this end pulley over here, this beam is the same one that's going across this structure over here. But then there's no beam between this initial beam and the pulley. There's actually a collar that's right here. So this collar is this extra space that's being substituted instead of having a beam like this initial one here. And so that's why there's a collar over there. And then you have your pulley, and then you have this last beam going across here. So this is kind of what I mean when I say symmetry of the robot, making sure that it's the same on one end as the other end. And so as you can see in this example over here, this beam is pretty much the same thickness as this 0.5 standoff as is this collar here. And so having the students just kind of think about, all right, are we matching the same width and thickness from one end to the other? And so to me, I think symmetry is it's a very important concept for the students to understand, especially when building their VEXiQ robots. I feel like once you get the symmetry right and almost perfect in a way, I feel like a lot of the things just kind of fall together. There's not going to be a whole lot of trouble when the students are going into the competition. They're not having to constantly fix their robot or anything like that. So it's all of this attention to detail that I think it'd be good for students to understand when they're building their VEXiQ robots, whether it's for class or for competition. And all right, I'm pretty early on my time, but I'm going to open up the floor if there's any questions from anyone. So again, these are the types of things that we reviewed: engineering notebook, some gear ratios, drive bases, and mechanisms. And of course, if you have any questions after this webinar, feel free to email me. That's my email there below. But yeah, I'm going to open up the floor if there are any questions at this time. You can feel free to type it in the chat or even unmute yourself.
Hey, Adria, it's Barry from St. Catherine and Morgan Hill in California.
Hey, Barry.
Hey, so in the engineering notebook, how do you get the students to record kind of the individual meetings that they have? So the first competition is usually like 8 weeks in, 6 to 8 weeks in. So they've met probably 10, 16 times. How do you get them to record that in that big long chunk for their initial meeting, for their initial competition?
So I know that my students, the way that they recorded their team meetings is either through Google Docs, or each of them kind of wrote it out on a whiteboard. And that was when we kind of consolidated all of the notes together. So I like to think of it where we're not recording, say, every single thing that every single student wrote about, but of course it's like breaking it down and figuring out sort of the core of what is needed in the actual strategy or robot design. So in the beginning, of course, we always talk about what is the game strategy? How do you want to play this year's game? And then looking at how many points do you folks want to score, and then documenting those types of things. So it's always sort of the core aspects of each section of the notebook. So I hope that answers your question.
And yeah, and how have you been doing there's a requirement that they record the time and that they have it, it's like the dates of when they were doing things and signing the book. With a physical book, it's like super easy, right? You just basically date it at the bottom, all the pages are numbered. But for the electronic notebooks, it's obviously really easy to go back and edit an earlier page in the notebook. But there are 5 points dedicated to in the notebooks for the judges to give to notebooks that are definitely in order, and the date timestamps. For the electronic notebooks, how have you been handling the date timestamps?
I know before this year we haven't seen a whole lot of digital notebooks from our teams here in Hawaii, but I know that last year when we went completely digital at the state championships last year, I know that I still had the students record the dates. We actually use Google Slides for our engineering notebook, so recording the dates and also recording the initials of who actually recorded that page of the notebook. But yet, when we submitted the digital notebook, we also submitted the revision history as well. So giving the judges sort of the sense that we've been doing this since, July, August, up until February, March, whenever states was.
So you actually took the revision history and created a snapshot of that and sort of stuck that in the last slide of here's the snapshot of all of the pages, just so to prove that you've done it. Okay.
Yeah, exactly. So yeah, I had the students create, pretty much take a screenshot and put it into a Google Doc or a Microsoft Word document and create a PDF of that. So we actually submitted 2 things for state championships, which was the PDF of the digital notebook and also a PDF of the revision history.
Okay, cool. Yeah, because we've had a bunch of competitions where we've done judging, and it's like 5 points or no points, right? There's no like, well, they put the date in, but there's no proof that that was the date, so they get 2 points, right? So it's like it's 5 or nothing, and it can be the difference between winning excellence in design or not, right? I mean, the 5 points is a huge swing. It's the number of points of expert in the in one of the other sections. It's a huge, can be a huge swing.
Yeah, I totally understand that. Yeah.
So you've moved away from digital notebooks for this year?
Yeah, I think most teams have moved away from digital notebooks. I just did VRC judge advising at a past tournament, this weekend's tournament. There were no digital notebooks submitted from any of the teams in Hawaii. So I think everyone is trying to get back to normal with using physical notebooks.
Right. Yeah, I've seen a bunch where people are doing the physical notebook and then just taking a picture of each of the pages and putting that into a Google Doc, right, or a PDF.
Yeah.
Cool.
I've seen that too. All right. Are there any other questions from anyone? Okay, so I guess we'll give everyone kind of a 5-minute break. And then how about we come back at the 50 mark for everyone. And we'll have Kelsey also set up her presentation as well. All right, thank you, everyone. We'll see everyone back at the 50 mark.
Cool.
Hello?
Hey.
Sorry, I wanted to ask a quick question. It's kind of a little strange topic. Two of us are from Japan now, and we are wondering if the engineering notebooks for competitions, if like grammar or things like that are taken, because we teach Japanese children who are not native speakers. So if they are writing in the book, should we be checking for grammar, things like that, or just let it go however they write it?
Oh, I'm not sure how to answer that from a judge advisor standpoint.
So the way I look at that one, if you don't mind, Adria, I'll take a shot. So the way that I look at it is, no, we don't care about grammar. We care about are they following the process? Are they documenting what it is they're doing, how they're thinking about it, what they're putting into that process, the sketches of what their mechanism might look like and the alternatives of that sketch, why they've chosen one mechanism over another mechanism, if they've done testing, recording of the results and showing why there's a winner. If that's written, I mean, a lot of that is pictures, a lot of that is charts. If the sentences are not grammatical, the judges aren't going to read necessarily every single sentence that's in the book, but what they're looking for is general flow, and also looking for, have the students followed the pattern. Grammar, I would say, is probably the last thing that we're looking at, and certainly I would never mark a student down for a grammatical error. That's not what the process and the whole the whole VEX scheme, whole REC scheme is about, right? It's about teaching them critical thinking, about teaching them engineering process, critical design process, structural engineering, programming, math, right? All of those things are the things, you know, whenever I look at a design notebook from someone who's a non-native English speaker, you know, I'm not looking for grammar at all.
Yeah, I agree with you, Barry. That's totally right. I mean, it's kind of nice to see some grammatical errors in there. We want to look for a nice, good, also slightly imperfect notebook in a way, because we know that that's genuine and authentic students' work.
Yeah,
especially at a VEX IQ level.
Yeah, exactly. When they make an error and they realize it's an error, a single line through the words and then write the next sentence, because then the judges can actually see what it was they originally wrote and then see how they revised it. So if they wrote the wrong thing, don't black it, don't white out or anything like that. Don't like smudge, you know, completely scribble it out. Just a single line through the sentence, and then write the next sentence, or even a box around it and a big X through it, so you can see what they originally thought and then how they revised the thought process in the documentation. Yeah, and errors, if it's too perfect, you kind of start to suspect that the coaches might have written it, right? And you know, we kind of expect there to be errors and that, you know, it won't be well formatted and there will be grammar and spelling. I mean, half of these, especially when they're not typed notebooks, the spelling is great. It's one of the funnest parts actually of looking at the notebooks, is how they spell some of the things, because you're like, okay, that was interesting. I get what they mean, but that's an interesting way to spell that.
Yeah, I think when I was reviewing a VRC notebook this past weekend, instead of writing channel, it was Chanel. So it was like 2 Chanels like across their chassis. So those are great. But yeah, it's like Barry said, it's all about that student design, learning, thinking process that we want to emphasize. And I think RECF and VEX Robotics have done a great job in emphasizing that over the grammatical, trying to make everything super perfect. So
yeah, there are no points allocated in the rubric. If you look in the rubric, there is no mention of grammar or spelling or any of that, but there are of all of the other things that we just talked about. But yeah, there's no points off for bad grammar, no points off for bad spelling.
Hi there. Sorry, this is Andy. I just wanted to add to this. Hi, Adria. Thank you again for hosting, and thank you, Barry, for adding that. Wanted to just share a little bit of experience here as well. I'm actually from VEX, so but I'm not from the REC Foundation. But there's been instances overseas, as VEX and our competition is global, is that there's going to be students whose native language, of course, is not English. So just wanted to point out again, the engineering rubric does not state if English is mandatory, and it is possible in the updated judges guide that if a language is used as not common where an event is being held, it's the responsibility of the team to provide judges with a translation along with the original notebook, or provide the original language version on its own with understanding that judges may not be able to understand written text as thoroughly. So those images, the examples of their code or images of their robot are so important. So please encourage them to use visual aids in order to express their thoughts if they're not comfortable written. So I just wanted to share that.
oh, thanks, Andy. I kind of interested to see in the future if we can get some, multiple language engineering notebooks here.
Yeah,
Right,
actually we did. Hi. Yeah, Andy, you first. Sorry. Yeah, I'm Kelsey. I'm also from VEX. I'm not from REC, but I've been judges for several events in Asia Pacific area, and especially I just went to one in China. Actually, there are a lot of students, their engineering notebooks actually are in Chinese, because the judges are, Chinese. But of course, if they go to like World Championship, they have to, provide the English one. But for the, the nationwide competitions, we actually encourage students to do the engineer notebook in their local language. That way can show their, the design process and everything. Yeah, it's language is not a barrier. Yep.
Thank you.
All right, Kelsey, I think you should be able to screen share, so the floor is all yours.
Oh, thank you. Yeah, let me share my screen. Give me a second. Okay, cool. Is everyone able to see my screen?
Kelsey, we're seeing your notes, not
Oh.
the presentation yet. So
Sorry, yeah, let me do that again. Works this time for everyone? Okay, great. Yeah, just a little bit introduction of myself. I'm Kelsey, based here in Hong Kong. I'm the education manager of VEX Robotics, supporting educators in APAC region in implementing like STEM and robotics competitions for students at all levels, from kindergarten all the way to college level. And I've working in this industry for like over 10 years, but a lot of my past experience are in English language teaching. And because a lot of like robotics teachers and educators and mentors are not actually from engineering background. So my experience could, share a little bit with you that you don't need to be like engineering background, to be a coach or to be educators in robotics. Well, of course, you need to study a little bit about those programming and all those like engineering and systems of robotics, but just encourage everyone, actually, you can be a robotics coach or mentor. Yep. So today I'm going to provide you introduction to sensors and programming using VEXcode IQ. This is an introduction section, actually session to the programming and sensors. I know like some of you here are really experienced. Yeah, but this is quite an introduction level. I know some teachers probably new and some are really experienced. So I'm going to first share a little bit of the VEX IQ generation 1 and generation 2 comparison. As you probably know, we have just launched the VEX IQ second generation. So I'm going to tell you the comparison, like what are the differences between the two generations and what we have updated. And then I will spend a little bit time to help you get started with VEXcode IQ, especially some of the new function we've got for the second generation. Then it's the introduction for VEX IQ generation 2 sensors and a little bit of programming. And then I will be able to share you with the available resources for educators, because we have provided a lot of like free resources for educators, and you are able to do a lot of like self-learning. All the resources are there. Okay, so today we're going to share about this, the IQ we're talking about today is actually the mid-level of our like VEX continuum. So all our programs actually ranges from kindergarten level, VEX 1, 2, 3, all the way to college level. I just wanted to show you this continuum chart to let you know, actually we have the solution, the STEM solution for all ages. Continuum is the key, we emphasize here, because we want students to be able to start exploring basic logic from the very young age. And along the way, they will be able to, perfect their skills and to learn STEM in-depth knowledge of STEM and also like robotics and coding skills. Okay, so about this chart, this is the summary of the VEX first and second generations comparison. I'm going to walk you through like each category. The first one, robot brain, battery, and controller. We have updated all those three. Actually, I will give you more details, in later slides, like how those different, parts, how those different electronics parts have been updated. And for the motors, it's basically the same. So we have 4 motors in generation 1 and still 4 motors in generation 2. For gyro sensor or inertial sensor, as you're probably aware for VEX, like VEX IQ generation 1, we've got the external gyro sensor. But for the second generation, we actually have improved the functionality of the sensor, and it is a built-in inertial sensor. So it's inside the brain. And actually, the second generation is actually located in the brain, and it has a 3-axis gyroscope and a 3-axis accelerometer. So the original gyro only has a 1-axis gyroscope. Also, the gyro and the second generation RoboBrain drifts significantly less while providing, better heading accuracy over time. And then it's the color sensor for first generation IQ. For second generation, we call it optical sensor. So with improved capabilities, it has the similar function of the color sensor, but it has some like other functions as well. And the new optical sensor has better performance in like low light conditions, and can now detect gestures as well. I will give you more details in later slides. And what also has been improved is the distance sensor. For the distance sensor, the original one actually used the ultrasonic rangefinder, and the new distance sensors actually use a safe class 1 laser, providing accurate distance measurements. So you will find the new distance sensor much more repeatable, due to its very like natural measurement beam. And the touch LED and the bumper sensors are pretty much similar for two generations. The most important thing, actually, it's not about, one is about the improved functionality of those functionalities of those electronic parts, and the other one is the storage. As you can probably see from this image, we have provided the storage for teachers. So this is really easy for educators, easy for classroom management, and also easy for students to navigate different parts. We have color coded, all different parts. It's really easy to organize. And there's a pin tool there is really user-friendly for students to assemble and disassemble different parts. And also you can see we've got, color-coded all the angle parts, the 30-degree, 45, 60, and 90-degree angle parts. As you're probably aware, for the first generation, sometimes it's difficult for students to find the right angle part. It's, the same color, and now it's been color-coded. It's really easy to locate different parts. And also we've got the chain and sprockets for the second generation, and new types of shafts, different lengths of like plastic shafts are color coded as well. Yeah, and a couple of like new standoff connectors. Not go into details for that. Yep, and this is the classroom bundle. Yep, all in those bag. It's really easy for teachers to carry. Unlike the first generation, a lot of like boxes, sometimes a little bit for teachers to manage. Yeah, so I'm going to a little bit detail about the RoboBrain comparison. So for the RoboBrain, the first generation, it's for the smart ports is similar, like 12 ports for both generation 1 and 2. And for the screen, that's what we've changed a lot. For the second generation, it's actually a color screen, just like this. So it's color screen. As I mentioned, we have a built-in inertial sensor now. It's the 6-axis built-in inertial sensor, and we don't have the external, for this one is we've got the built-in Bluetooth, so you don't need to, buy external Bluetooth and plug in, because a lot of times, the Bluetooth could be, have some problems, and now it's definitely built in, so it's really easy to do pairing and other stuff. Yeah, so this is Bluetooth 5.0, and the CPU speed has increased a lot as well. In terms of coding, I will show you the platform in later slides. So for generation 1, you are able to use Robot C and VEXcode to code, but for second generation actually moved away from Robot C, and now you will need to use VEXcode. But we have added like Python and C++ to the platform. So students can do, block coding and text coding, and, they can simultaneously they can, change from block coding to Python or C++. So it's the same for all our platform now. If you're aware of our VEX VR, the virtual robot platform, VEXcode VR, it's also got block and text coding. Yeah, and it now has the micro SD card, so you can extend your memory, and that would be, help you to store more things to the robot brain. Yeah, and what's more, we got like multilingual languages, support multilingual languages on the robot.
I don't know if we've lost Kelsey or not. I hope that I'm just the only person here, but let me see about
We lost her. Yeah.
Apologies, let me get her set up again.
Hi. Can hear me now? Yep. Sorry about that. Yes. Really sorry about that. Something wrong with the office network today. Yep. Okay. Let me share my screen again. See if you are able to see my screen.
Perhaps just to turn off your video feed, but keep your screen, that might help, Kelsey.
Yep. Doing that now. Apologies. Yes. Oops. Yep, just let me know if I lost my screen again. Can you see my screen now? Okay, good. Yep. Where were I? Okay, cool. So just wanted to mention that we have like multilingual now on the robot screen, providing like different languages on the second generation. Yep. So, and there's the indicator lights on this VEX IQ brain, and I'm not going into too details for that. It's just like different color, like solid green, it means the brain is on and the battery level sufficient. And if it's blinking green, it means the battery level is also sufficient, but controller connected. And if it's like blinking red, it means battery level low. So you will be able to find all this information on our knowledge base. We call them STEM lab. So all available online. Yep. And then what I want to emphasize here is about our robot battery, like the second generation has improved a lot. The capacity has improved. Sorry, the capacity hasn't improved, but the we are using a different chemistry. It's now actually a lithium ion battery now, so it's what you use for your phone and a lot of like laptops. So that's the common technology nowadays. And what's more is the charger. The way we charge the battery now, it's USB-C. It's the same for the battery, the same for controller, and for all our other platforms. So using USB-C is really user-friendly. Okay, so now, as I mentioned, this is like USB-C, and you can actually, we've got the indicator lights as well. So like if it's one light, with one light, it means like 0 to 25% charge. If it's like 4 lights, it's 70 to 100% charge. So you've got like full battery. Yep. And then it's the controller. The controller, what we have actually improved here, we actually added with 2 extra joysticks click buttons. So perform all different functions, and you're able to code like the joystick click buttons. Also we've got the wireless programming with faster downloads now for the 2nd generation, and the charger, as I mentioned, it's using like USB-C. For the radios, no more external Bluetooth plug-in. So it's everything now is built in, and controller, and also, you know, the brain. Yeah. So as I mentioned, this is the USB-C charger, and you don't need to prepare a different cable for you to do like charging or connect to your VEXcode IQ. Yep, and this is the power. Different color means, you know, your battery level, and also like the LED indicator lights shows you whether it's completely charged or not. Yep, not going to details for that. You're able to find everything on our knowledge base. Okay, so now it's wireless pairing with the controller and brain, and you no need to use a cable. So it's simply by, you know, using 3 fingers, and then you will be able to do the pair up. I guess some of you will receive your new IQ 2nd generation soon. Yes, and what I want to mention here is actually the compatibilities for VEX IQ 1st and 2nd generations, because I know most of you still got the 1st generation, but don't need to worry too much for that. Everything works with everything except for the chargers. The RoboBrain, like 1st and 2nd generation, work with both IQ Robo batteries, and the and also it works with both IQ controllers, 1st and 2nd. So literally everything works with everything. And also the sensors and the smart motor as well. You know, it's the only difference is the charger. Because they use different chargers. The 1st generation battery chargers were not harmed, but were charged the 2nd generation batteries. But the 2nd generation charger connects via USB-C. Okay, and then I will go to the programming part. Before I show you the VEX IQ, the code, VEXcode IQ, I just wanted to show you this continuum. This is actually our software continuum, and showing our, you know, programming education pedagogy, which provides you the solution for the STEM. Yeah, so actually it provides students for all ages to participate in learning code that makes this robot work. As you can see from tactile, that's our entry level. So students are able to do programming without, you know, without the screen. So they can programming it on the robot itself, and then to VEXcode Go, that's our 2nd level, and then to IQ. And so that's, they can program use block coding and also text. Well, and then student can move up to the text-based coding, and to, you know, VEXcode V5, that's the next level. And they can actually see in real time the C++ or Python code generated by each block added to their project. And they can also like convert their block-based project to a text-based project with a single button press. I'll show you in a later slides. Yeah. And at the last, you can see we call them VEXcode Pro 5, V5 actually. So that interface provides students with the same tools and programming languages that professionals use every day. So this continuum we wanted to emphasize, it's actually all the platform is consistent across all levels. So students progress from, when they progress from like elementary, middle, and high school, they never have to learn a different block, coding, or toolbar interface. Yep. So this is the VEX IQ 2nd generation. the new one. Let me show you. Probably I use this platform to show you a little bit first. As you can see, we now have the block coding and also C++ and Python. And so students are able to choose between the 3 different coding languages, and they can develop their programming skills with a lot of like integrated examples and helps and tutorials as well. So this is the same, is available for Chromebook, iPads, Android tablets, Windows PC, and Macs. Yep. Let me go back to this, actually sharing the platform with you. Okay, I guess everyone is able to see this platform. Just probably a little bit. Oops. Yeah. Okay. You are able to see this platform, right? Mm-hmm. Okay, great. Okay, so this platform, I guess most of you are probably, very familiar with this. I just used like probably 2 minutes just to walk you through a little bit for those teachers who are new to VEXiq. You're able to choose different languages, and you can open a new blog project or new text project. So if you click new text projects, now you're able to select, whether to do a Python projects or do a C++ project. Yep, so that's the differences. And for the tutorials, so it's the same for VEXiq as VEXiq first generation. You're able to, learn how to do those basic programming using the those tutorials. Yes, and for the slots, now you are able to save like 8 programs to your slots. And what are the differences? Probably just a little bit of that. And you can see from the print console here, you will see, simultaneously the real-time coding for C++, those languages, and Python as well. Yeah. Basically, those are what we have improved. The last thing I wanted to mention about this platform is actually you can learn a lot of different coding and programming using the examples. For example, you open examples here, and now we have added, second generation. So if you want to see those example programmings for first generation, you can select here. And if you want to know those second generation, because we have added some sensors and improve some of the sensors and functionalities, and you will be able to find the examples here. Yeah. Okay, so I'll come back to this platform later, and now I will go back to that presentation. Okay, so now I will start introducing the different sensors. So for VEXiq second generations, there are 5 external sensors. The first one is optical sensor with improved abilities, and the second one is distance sensors with improved capabilities and functionalities. And the third one is touch LED. It's the same as first generation, and bumper switch is the same as the first generation. And as I mentioned, we have a built-in inertial sensor now. Yeah, and I will introduce them one by one. The first one is the optical sensor. So for the IQ optical sensor, the second generation is actually a combination of the following 3 sensors. The first one is the proximity sensor. So it can do proximity detection. It can detect when an object is near or not. So the proximity sensor measure reflected infrared energy source from an integrated infrared LED. As such, the values will change the ambient light and objects reflectively. So that's the, the proximity detection. And the second thing it could do is like color detection. It can report regular color, hue, and also a couple of other things. It has the color sensor. It's actually the color information is available as like three colors, red, green, and blue. Hue and grayscale and color detection actually works best when the object is closer than 100 millimeters. So that's the color detection function. And the third one is light. It can report ambient lights. It also has LED on it. So it reports the current amount of ambient light that the sensor is detecting. This could be the brightness levels of a room or the brightness level of a particular object. For example, you can do like line tracking using this light, sensor. And as I mentioned, this optical sensor also contains white LEDs, 2 white LEDs in this optical sensor, and this LEDs can be turned on and off or set to a specific percentage of brightness. This provides a consistent light source when detecting colors, regardless of the surrounding light conditions. Yep, so those are the 3 functionality, I mean, the big categories.
Hey, Kelsey, can I ask a question?
Yeah, sure.
So is all of the functionality for the optical sensor available in all of the programming languages? Because the old optical sensor, you could only turn the lights on if you were using Robot C, but you couldn't turn them on in IQ. There was like some features that weren't available in blocks versus C. Is everything available in all the languages?
Yes, everything is available now on the updated VEXIQ. Yeah. So have you updated your VEXcode IQ yet? Yep.
Yes. Yeah. No, we're on generation 1. So
generation 1. Yeah.
Yeah.
No worries. Yeah, everything is available on VEXIQ. VEXcode IQ. I mean the updated version.
Yeah, we're on the latest version of VEXcode. Yeah. Okay, cool.
Now, bear in mind, we will also be pushing out updates as bugs are discovered or as we're looking for process improvement in our programming. So please bear in mind is that we also have a change log that's listed on our website for downloading the program. So if you download it, you'll be able to have much more functionality rather than just web-based, browser-based codeiq.vex.com.
Yep. Yes. In order for the optical sensors to be functional with the IQ brain, the sensor smart port and an IQ brain smart port needs to be connected with the smart cable. So it's similar, I mean, as generation 1. And actually the optical sensor will work with any of the 12 smart ports on the brain. And when connecting the smart cable to the ports, be sure, the connector is fully inserted into the port and the connector's locking tab is fully engaged. Because a lot of times students will, tell you, oh, it's not connected. It's because it's actually not fully inserted. That's a common, problem or issue students always facing. Yeah. So the optical sensor receives light energy and converts the energy into electrical signals. So the sensor's internal electronics converts the signals into output signals to be received as an input by the IQ brain. So that's how it works. The optical sensors, and you can mount and you can be mounted on a structural parts like this. Yeah. And for the configuration and how to add the optical sensor as a device in VEXcode IQ, it's pretty easy. If you have done, VEXIQ before, it's just add a device and select optical sensor. Yeah. But for this IQ robot brain, just be sure you will need to choose between first generation and second generation. Yeah. And it's able to, as you can see from this image here, it's able to report the brightness, the hue, and the color it's detected. And you are able to, set the light on or off. And you can also, set the light power to 0 to 100%. Yeah. So as that's the question Barry asks, whether it can set the LED light on or off on the on the VEXcode. The VEXcode IQ, the answer is yes. Okay, so just to show you, this is the second generation, and just to show you this one, the placement actually of the optical sensor is very important to obtaining accurate like readings. So this one is mounted on top at the front. So actually you will need to be sure no structure on the robot is in front of the small optical sensor window on the face of the sensor. And there needs to be a clear path in front of the sensors between any object being measured and the sensor. Well, the proximity sensor measures, as I mentioned, reflected infrared light intensity. This will cause the values to change the ambient light and object reflectively. So that's the way they measure the color and everything. Yeah. So this is the second generation, the built-in one. And I wanted to show you this one actually on the robot brain. Yeah, because I'm really sorry, like the network is very bad today, so I'm not able to do like live demo, but just using these videos and images, print screens to help you navigate. So actually this is the second generation brain. As you can see, it's color and it actually shows a lot of like data. It's really helpful to use the device's screen on this IQ brain to see, those information of the optical sensor is reporting. So here, what you can see the LED, the brightness and proximity and hue. So what I wanted to emphasize for this slide is the proximity. So the proximity of an object is near or far. It's actually shown on the screen. You can see the proximity near. So it will change in real time when an object is near. If an object is far, it will show far. So actually the sensor's color detection works best when the object is closer than 100 millimeters or approximately like 3.9 inches. So you will be able to find all those data on the robot brain. Yes, for this one, like you can see different, this can show near and the other one can show far. Yeah, so not go into details for that. Okay, so some very basic programming, what can an optical sensor do? The first function is to detect an object. So this feature allows your robot to detect an object when it becomes within the range of the optical sensor. So this example project shown is used to code a robot with an optical sensor mounted on the front. Okay, as I mentioned, the location is really important, where to mount the sensor. So these sensor is mounted on the front. Okay, so this explains that the robot will drive forward until it detects an object, such as a cube or other like stuff, and then stop driving once the object is detected by the optical sensor. So that's the first usage of the optical sensor. So whether like found an object or not. So this is pretty, simple programming, the use of optical sensor. I'm going to show you an example, the moving. I'm going to actually plug in this robot brain, and then you will be able to see the behavior of this robot with this coding. Actually, so these example projects shown on the left is to code this robot with an optical sensor mounted on the front, as I mentioned. And so it will drive until it detects an object and then stop driving once the object is detected by the optical sensor. And also you can see on the print console, it will print the object found on the print console. Yeah. And let's see that in action. And that's, yes. It stops when it's found an object and it's printed on the print console, object found. Yep. So this is the first function I wanted to highlight for this optical sensor. Yes. And next one. I mentioned about the data shown for proximity, and now I wanted to mention hue. Well, actually, it's the hue is, the value between 0 to 355 degrees. It reports. So on the left, actually, the purple shows like the hue value is 248. It's purple, and on the right, it's the hue value reports 348. So it's actually reporting the hue value, and you can actually identify that the different hue value by using the color ring down the bottom. It shows the different degrees of shades and colors. Yes, and each hue value has a color shade association. And this feature actually allows your robot to provide a number for the hue of color of an object. It provides actually a more precise measurement of color as compared to a generalized, green, red, or blue, because, there are a lot of different colors in different color shades in like red, blue, or green. Yes, so this is how it reports the hue on the robot brain. Yes. And another function is the detect a color for the optical sensor. That's the main function for an optical sensor. This feature allows the robot to identify the color of an object. Let's see an example project here. So this is an example project. It shows a robot with an optical sensor mounted on the front and a touch LED attached to it as well. So there's a touch LED, as you can see there. The white one. So once an object is detected, the robot will glow the touch LED, the color of the object detected. And so you can see if, the optical font and color, if it detects in red, the touch LED color will be, the touch LED will green red. Yes, it shows, and now it's red, and it's also will print on the print console, the hue of actually the color. Yes, so now it sees the red cube, and the hue is 356. So this is the hue of the red, as we actually tested before. And now we wanted to see another different colors, like the green cube, whether it can detect. Let's run the project. Yes, when it detects the green, the touch LED glow green, and then the hue is 126. So that's the color shades for the green. Yeah, so that's the way how this, the color coding optical sensor, the color detection works. And you can just use those programming basic one, like conditional if, then, and else if, those like basic block coding. Now it's the detects the color blue, and the touch LED will glow like blue. Yeah. Okay, I'm not going to show this one to you. It's similar functionality. And the next thing I wanted to mention on this robot brain is the LED color, the percentage. So the LED here, this data, it shows the current brightness percentage of the LEDs. So it ranges from 0 to 100. So 0 means it's off, and 100 means it is fully on. And the next one is brightness. It also shows the percentage of brightness of the ambient light in the room or of an object. For example, this one, the LED, the current brightness is 100%. Is 100, which means the LEDs is fully on, and the brightness level is 3. So it means the percentage is 3%. The ambient light, it detects it. Yep. And now I wanted to show you another function to actually show the brightness of this optical sensor it detects. So the optical sensor is mounted. Now it's pointing down. As probably you can see, well, it's not that clear from this video, but it's actually pointing down the optical sensor. So that way we can, we can, see the brightness and detect the brightness of the ground surface. And you can see now it's on the white surface, the brightness is 20 something. If now the optical sensor is on the dark line, the brightness shows it's around 3 to 5 something. So that way, we can actually do line tracking using this function. So let me see this, and you can see that's for this programming, we allow that robot brain to print the brightness on the print console. Yes, so remember on this bright, the white field, the brightness around 27 something, but of course each time is different because it actually happens simultaneously. And if it's on the dark surface, it would be around 3 to 5 something. And we can use this to do line tracking, which I will show you a demo in next slide. Yeah. Okay. So this is the usage of actually a line tracking. So as you can see from the programming here, first we need to set the optical sensor light on, and then we need to set the optical light power to 100% or whatever percentage, but the brighter the better. And if the optical sensor detects, if the optical sensor, the brightness is below 15, the below 15 means it's like dark surface, dark line. So we want the actually robots move to the right. If it's on the dark surface, we want it to move to the left. If it's on the white surface, so it's bright surface, we want the robot move to the right. So this allows actually the line tracking function, allows the robot to move back and forth to follow the line. Yep. See if you are able to see this one. Oops. Yes, so it is doing line tracking now using this optical brightness detection function. Yep, let's see that again. When it's the light surface, it will move to the right, and when it's the dark surface, it will move to the left. Yes, so this is the line tracking function. There's some basic programming for that, and you can copy that. And well, of course, you will need to do testing first. Well, what would be the brightness level on the white surface, the bright surface on your end, and what would be the brightness level on the dark surface on your end? So it varies, between different surface. Yeah, and what would be the uses of the optical sensor on a competition robot? It actually provides an excellent competitive advantage for competition robots. Like the ability to detect objects and their color will provide a great deal of information when designing autonomous routines. So an object's presence and hue of color will actually provide helpful information with detection of game pieces or goals. For example, in this year's pitching in a VEXIQ challenge, an optical sensor could be angled to scan your robot's intake. So it can be mounted here. So as soon as a ball is detected in the intake, this could automatically turn on the robot's arm to launch the ball. So no matter what the application the VEXIQ optical sensor is used for, well, it will be a welcome addition for teams. It's definitely useful and helpful for your competition robots. And it's actually the sensors value are open for the imagination of the users as well, and they can think of other ways to use this optical sensor to equip their competition robot. Yeah. And the next one I wanted to tell you, share with you a little bit is the IQ sensor, the second generation, the improved one. So it's actually the technology is different now. So for this generation, this sensor uses a pulse classroom laser, classroom safe laser light to measure the distance from the front of the sensor to an object. And there are 4 functions for the IQ distance sensor. The first function is to detect object. It can be used to detect when the object is near or far. Yeah, and the second function is measuring distance. As I mentioned, this uses the laser light to measure distance from the front of the sensor to an object, and the distance will be reported in inches or centimeters on the brain sensor dashboard, and in inches for the millimeters in VEXcode IQ. The third function is determining the object relative size. This is a new function for the second generation. It can be used to determine the relative size, like whether it's a small, medium, or large. So there are 3 sizes available to be detected. And the fourth function is to report object velocity. The sensor can be used to calculate and report the velocity in meters per second for an object approaching the sensor, or the sensor approaching an object. Either way is fine. So the object velocity in meters per second. Yes. So those are the 4 basic functions for this distance sensor. So the sensor's measurement range is 20 millimeters to 2000 millimeters. But actually when below 200 millimeters, the accuracy is approximately around like 15 millimeters. Well, above 200 millimeters, the accuracy is approximately 5%. So we'll actually, yeah. And then it's about the placement. Well, as I mentioned, the placement of sensors is really very important. And it's similar to optical sensors. Be sure no structure on the robot is in front of the small sensors window. That's the window there. That's where the distance sensor is located. And there needs to be a clear path in front of the sensor between any object being measured and the sensors. Yes, and it's the same on the RoboBrain dashboard. The distance value is able to be shown on the dashboard as well. So basically all the data of all the sensors will be shown on the Brain dashboard. So this is really helpful. The way to configure and add this distance sensor is quite similar to all other sensors. And as you can see from the programming there, those block coding, and it can report the data of the distance, and also reports the object velocity and report the object size, whether small, medium, or large. And it can also report whether an object is fun or not. This is the first function, detect an object. It's pretty similar to the optical sensor as well. So this allows you to detect an object. So this example shown on this slide is used to code a robot with a distance sensor mounted on the front to actually drive forward until it detects an object. And then drive forward once the object detected by the sensor. Yeah, just wanted to show you, run this example to you. Sorry, just run this project. Okay, so it will turn right until it finds an object. It will drive forward. Yes, it's exactly showing what we do here. So this is pretty easy, simple, programming for how to do, detect an object here. So I'm not going into detail for this one. And this is distant to an object. It can report the value. This function actually provides a measurement between the front of the sensor and an object or a barrier. The example here show actually to code a robot with a distance sensor mounted on the front and a claw attached to it as well. The robot will drive until it detects an object is less than 75 millimeter away from the sensor, and then close the claw around the object. And this would be also helpful if it is known that there is an object in front of the robot and you want the robot to drive forward to collect that object. So that's quite useful in competition as well. And determine how far away an object is from the sensor and use that parameter in the project. And you can use the sensor dashboard on the IQ Brain. Yep. Just wanted to run this project to show you this. You can see it's print on the print console. Show the distance. No, it's the data actually will be shown on the robot brain as well. Yeah, either on the print console because you program that as that's like this is 240 something, and when it's close, it's 76. So you can see the data. Yep. And the next function is report object velocity. So this feature provides a measurement of the velocity in meters per second for an object approaching the sensor or the sensor approaching an object. So in order to observe the velocity changing with an approaching object, you can see this example. Information will be printed to the brain's screen. So the brain will print when an object is detected by distance sensor and the velocity of that object in meters or second. Yeah, to more accurately see those changing numbers, the print precision is set to 0.1 here. Yes, so you are able to set the actually the precision. Yeah. So you can test this project with moving a cube like closer and further away from the sensor. And when the object or sensor are moving away from one another, the velocity values will be negative. Yes. So every time when you print the data, you will need to set the precision to the brain. Yes. And then I wanted to show you how to determine object's relative size. This is a new function. This allows your robot to identify an object as being small, medium, or large, depending on the sensor's reading. So for this example projects here, you can see. So this is actually use the if then else and print blocks function to print the relative size of an object on the brain. So you can place various objects in front of the sensor and look at the readings on the brain screen to see the size identification in real time. I will show you the demo later. So, well, but in order to determine the relative size for the object using the sensor, the objects should be placed between 100 millimeters and 300 millimeters away from the sensor to get the most accurate representation of the size. Yes. So as you can see from,
see that I have three game objects here: a large object, a medium object, a large object, a medium object, and a small object. So I have created a program here so that you can see a reading on the print console if the object is small, medium, or large. So if it finds a small object, it's going to print small, a medium object is going to print medium, and a large object is going to print medium. And we'll watch that information change in real time here on the print console. One thing you should note is that I do have to have my robot plugged in order to use the print console, and that's why you see this cord here. All right, so it's right now reading the small object. If I move this out of the way, you can see it change to medium, and then it will change to large. Medium, small.
Yes, as you can see from this demo video, when the sensor detects a small object, it will print like small here, and if it detects medium, it will print medium, and if it detects large object, it will show large. So that's the way this sensor works.
See that I have three game objects here:
Okay, so what would be the uses of the distance sensor, the second generation, on a competition robot? So it will actually provide a superior competitive advantage for the competition robots. The ability to detect distance to the perimeter wall and be able to measure a robot's velocity will provide a great deal of information when designing autonomous routines. It's also in the autonomous routines. So object detection and determining the object's relative size will provide helpful information with the detection of game pieces or goals, like detection of the walls, detection of the ball. For example, in this year's challenge, pitching in, A distance sensor, second generation, could be mounted on the back of your robot. So here, just like it's shown on this picture, it can be mounted on the back to detect walls when driving in reverse. So this can help automate movements, especially when retrieving a ball into the intake, driving in reverse, and then turning to launch the ball into the goal. So this is pretty a useful like function for competition robot. We do encourage, students to add all different kind of sensors to improve the functionality for their competition robot. Yep. And now it's the inertial sensor. So we don't have any like external gyro sensor anymore. So everything is built in. So it's this inertial sensor now. How it's improved? So the built-in inertial sensor now has a 3-axis gyroscope and a 3-axis accelerometer. So you can see all the data here. The original one only has 1-axis gyroscope. And it's actually, I mentioned this updated one, the new generation inertial sensor actually allows the robot brain drift significantly less while providing better heading accuracy over time. So this one has different functions and can report different data, can report the heading, the rotation, pitch, roll, and yaw, acceleration along the XYZ axis, and rotation rate of rotation along the 3 axis as well. The first one it can report is the heading. The heading is the direction the brain is facing in. Actually, it's reported compass style using degrees from 0 to 359 degrees. So the 0 point can be set using commands in VEXcode IQ or by calibrating the VEX IQ, which is second generation brain. And well, this information can also be used to turn your robot to face a specific location when using a drivetrain. So in the sensor dashboard, you can see on your robot brain, heading is the first value listed here. So if you move the brain while on the screen, you will see the value like updated in real time. Yeah. So every time you move your brain, you will be able to see, the heading of the screen. Yeah. If you want to actually reset the heading of your brain, select, the check button on the brain, and this will reset the heading and rotation to 0 degrees. Yeah. And all the data on the inertial sensor dashboard will be based on this new starting location. Yeah, this is the heading. And the way you code it, I just give you 3 examples using block coding, Python, and C++. So you can turn to heading, you set degrees and set drive heading to degrees. And even for Python and C++, it's pretty, routine. It's pretty simple to do that as well. Yeah. It's really similar to the concept of block coding. So that's heading. And the second data it can report is rotation. So rotation is supported when the robot springs around the center axis of the brain. The amount of degrees reported on the sensor dashboard indicates the direction of the turn, and the degree value of the turns the brain has completed since calibration. So unlike heading, the numeric values are not limited to the 0 to 359 degrees. So the robot can rotate counterclockwise for negative value, or clockwise for a positive value. So on the left, you can see it's actually the negative value. So it's turns the rotate counterclockwise. And on the right, you can see the positive value, which means the actual robot turns actually a clockwise rotation. Yeah. So I'm not going to detail for that. It's pretty easy. Let's just simply turn to rotation and center degrees and degree. Yeah, just to simply set that. And the other one I wanted to mention here, it can report the pitch, roll, and yaw, the data, report the 3 axes. Actually, pitch, roll, and yaw are the orientation angle of the brain along a specific axis. The pitch, you can see here, represents the x-axis and the angle of the robot tilting. Yeah, forward and backwards. So this is the pitch, and values for pitch range from a negative 90 degrees to 90 degrees. So this is pitch, and the second one is roll. So a roll represents the y-axis, the angle of the robot tilting left and right. So values for roll ranges actually from negative 180 degrees to 180 degrees. And the third one is yaw. It represents the z-axis and the regular rotation of the robot. So the values actually range from negative like 100 and minus 180 degrees to 190 degrees. So those are the three functions. And if you wanted to know more about this, I'm not going to details for this because it takes a lot of time to explain like pitch, roll, and yaw programming. You can find the example project in the VEXcode IQ. Actually, the example project can be used to show how to detect the orientation angle of the brain along the three axes. Yes, so you will be able to find a lot more details using examples on this VEXcode IQ. And as I mentioned, it can also report the acceleration on the X, Y, and Z axis. Well, I'm not going into details for that. There's like too many functions for this. Not going into details for that. Yeah, just wanted to share with you a little bit of like the uses of inertial sensor data on a competition robot. It can detect which direction and how far the robot has turned from its starting point. It can detect if the robot is tilting up or down by mounting on the side of the robot. It also can be used to detect the status of one of the robot's components, like whether it's arm up or arm down. Well, of course, it will need to be mounted on the manipulator or attachment. So those are some of the uses of inertial sensor data on a competition robot. Well, but if you want to mount it on the manipulator or attachment, you will need to use an external like gyro. Yeah, you are still able to add like external sensors as well to this second generation. Yep. And for the touch LED and the bumper sensor, I'm not going into too details because those two sensors are the same as the first generation. Just wanted to summarize it here. For the touch LED, there are two functions. It can detect the capacitive touch, such as the touch of a finger, and can also be used to display colored light as well. So to start or pause the program at the touch of a finger, the basic use of it. Yes, this common use, or to display different colors at different parts of a program. So you can change the LED color to red, green. Yep. Not going into details for that. And then I just wanted to summarize the uses of touch LED on competition robot. It can be used to start a running program with a finger press. And team members can see when different sections of an autonomous program are running by programming the touch LED display a unique color for each section. When being judge of the competition, a lot of actually teams are using the touch LED. So to running the program, and using the touch can also be used to help like troubleshoot programming problems if issues occur. So it can report some issues with a touch LED like red, and it will alarm you, oh, there's something wrong with the programming with the robot. Yeah, and then the bumper switch is actually, the bumper sensor is actually a switch. It tells the robot whether its bumper is pressed or released. So when it's pressed, the sensor value is 1. When it's released, the sensor value is 0. Yeah. So how this works actually is based on probably the most commonly used electrical device. That's the switch. It consists of like 2 terminals and a wire bridge to make the connection when the switch is pressed. So as in this illustration, when you press on the connecting wire, you complete the circuit and the robot brain registers that in your program. So that's the way. Just wanted to show you how that functions. And the first function can trigger robot action when pressed or released. It's the same as LED switch, LED bumper. And the second function can detect walls or objects when the bumper runs into them. Yeah. Not going into details for that. So probably because we don't have a lot of time left, I'm not going to detail for this. Just wanted to show you the resources because I guess it would be really useful for you to, navigate all those, resources you're on your own. The first one I want to show you is STEM Lab. I guess you are already pretty familiar with that. So on STEM Lab is our like online education resources for educators. And we provided the free like pacing guide, teacher's notes, and even student facing PowerPoints. And we mapped our curriculum to different like standards, the US standards, the UK is the UK standard, and also like a lot of like different international standards. So for using this pacing guide, it actually can function as the plugin lessons fit into your existing curriculum. I'm sure I will send you this PowerPoint to you, and there are links there. So I'm sure a lot of you are familiar with our like STEM lab. So all the teacher available resources are there. Not going into details. There's one-on-one like VEX pacing guide as well. So including the suggested activities for VEXcode VR. So that's a free platform for you to code a virtual robot. So it encourages you to do like blended learning. You can use this to, to do some extension activities with VEXcode VR. And for the second generation, we've got like up to like 36 weeks of lessons. And overall, like there are 23 labs and 1 activity series divided into like the following subject areas. Not going into too details of that, just wanted to show you the structure. And for now, we have, it's different from VEXIQ generation 1. For now, we've also updated a lot of activity lessons. A lot of like those activities lessons are 1-pagers. So it's functioned as the extended activities for teachers. So you can use those to do a lot of like after school activities. So now we have like 37 activity lessons available for you. Even you're using IQ generation 1, you can still refer to those activities. A lot of them can also be used for generation 1 as well. So those are all on STEM Lab. And this, the free online certificate, I'm sure a lot of you are pretty familiar with that. The educator certificate is actually completely free and online, and you can learn it on your self-pace. I will send you the link to you. So it's actually available for all our like platforms. And this one is, I guess this is the most useful one for me, at least, is the STEM library. So it's knowledge base. It provides all kinds of skills and knowledge I need, like the electronics, mechanical, and even teacher resources, how to teach your students. So a lot of technical skills there, and also like how to do like issue troubleshooting, and you can find a lot of available resources there. So this is the STEM library. If you have any problems, or questions for the platform, I encourage you to search in the STEM library. You will be able to find most of answers there. Yep. And this is the PD Plus, a new this is a new platform for actually like educators. It's actually what's more, so this is actually a platform that enables educators to learn from and interact with experts in the classroom competitive robots. So we have actually videos for every platform, and including like pedagogy and the STEM knowledge and a lot of different videos. So what's more actually includes the tickets to the annual VEX Educators Conference held at the VEX Robotics World Championship in the US. So you will have the chance to participate in this exciting networking event with this VEX PD Plus. Yeah, this is another like professional development like platform for you. Yeah, and there are some like if you want to know more about competition resources, there are a lot of like available resources here as well in terms of build instructions, software, curriculum, event resources, and even like the forum. Yep. So basically that's it. Any questions for second generation or sensors? Yes. I saw Barry's question. Is the second generation brain capable of using the vision sensor? Yes, yes. You can use vision sensor for second
Can you
generation.
actually use it though? In the first generation, it took so much memory that the basic you could like do very, very basic things, but you couldn't actually use it on a robot, right? It was the brain didn't have enough memory to make it usable. So can you
yeah, because for second generation, you can add an SD card extension to your, brain memory. So that's how
okay.
you're able to use that. Yes.
Oh, so you can use the SD card to
Yes,
expand
yes.
the memory as well as to just for using it for device logging as well.
Yes, you're right.
Oh, cool.
If there aren't any more questions, so I'll give it back to Adria.
Thank you so much, Kelsey, for your presentation. I definitely found it very helpful. I just ordered my second generation IQ, going to be playing around with it when I have the time. But again, thank you, everyone. I'm so glad everyone was able to join. I've been checking up on some of the emails, and it looks like you needed a passcode. I thought I had taken that out, or I thought it was also sent in the registration. But thanks so much for joining. Today we recorded this meeting today. We're recording it right now. We're going to have it posted on YouTube, and then we'll share the link with everyone so you can share it with your fellow VEX Robotics colleagues as well. So I think I've also attached mine and Kelsey's email to that original email sent. So if you have any specific questions on anything that we've talked about today, feel free to email one or both of us. And again, thank you everyone for joining us today, and hope you have all a safe and holiday season. So thank you, everyone.
Thanks, Adria.
Thank you. Bye.
Look at it.